welcome back to the course. In the last two videos, we discussed about the definition for heat, thermodynamics versus heat transfer, and we discussed about the conduction heat transfer mode. I've defined the formula and units for various terms we defined. Now, this class, let us discuss about convection heat transfer. Convection heat transfer is the second mode of heat transfer. So, it's called as CONVECATION, convection heat transfer. It is nothing but it is defined like this. Heat transfer between a solid surface and adjacent layer of fluid which is in motion. This is the definition for convection heat transfer. Convection can be seen as conduction plus fluid motion. The fluid motion is very, very important. If there is no fluid motion in the fluid, like in the liquids or gases, then that will be purely by conduction. If heat transfer occurs through a fluid layer which is not in motion, that should be only by conduction. And this fluid motion is sometimes viewed as advection. So, conduction plus advection. Some people say these two words are coined together to form the word convection. So, if here the fluid motion is very, very important. Fluid motion is very, very important. If the fluid motion comes because of external source, then it is called as forced convection. So the external source can be fan, blower, etc. When fluid motion comes because of buoyancy force, which results because of density difference, which comes into picture because of temperature difference. Then it is called as natural convection or free convection. Both of them require fluid motion. If you use an external source like a fan, blower, etc. For making the fluid motion, that is called as forced convection. And if it comes because of buoyancy force, which is created by density difference, which is created by temperature difference, then it is called as free convection. Another name for free convection, natural convection. So, fluid motion is must here to have convection heat transfer. Now let us discuss about the governing equation for convection heat transfer. Governing equation for convection heat transfer. So, let's take an example of a simple plate whose thickness is very, very low, such that heat transfer from the edges are negligible. Assume that this plate is at temperature Ts, and we measure the fluid temperature, surrounding fluid temperature far away from the surface, which means the hotness of the plate. Assume that the plate is at high temperature. This hotness is not having any influence over the fluid here. And let this area from which convection is occurring, let this be AS. AS surface area. Now we define convection heat transfer Q convec as rate of convection heat transfer is directly proportional to the temperature difference Ts minus T infinity, where Ts is surface temperature, T infinity is temperature measured in the fluid far away from the surface, and it is also directly proportional to the surface area. If I increase the surface area, convection heat transfer increases. If I increase the temperature difference, convection heat transfer increases. Rate of convection heat transfer increases. So rate of convection heat transfer, so the proportionality constant is called as H. H into A suffix S into Ts minus T infinity, and H is called as convective heat transfer coefficient. Convective heat transfer coefficient. Coefficient. Well, let us work out for the units of this formula. And this equation is called as Newton's law of cooling. This is called as Newton's law of cooling. So this is called as Newton's law of cooling. Let's check for the units. I repeat the formula once again. Q convection is equal to H into A suffix S into Ts minus T infinity. So we know Q convection is rate of convection heat transfer, and its unit is rate of convection heat transfer, or convection heat transfer rate in simple words. Its unit is watts, because it is rate, joule per second. We are not speaking about amount. Here we are going to speak about rate of heat transfer. And AS, it is surface area from which convection heat transfer is occurring. Surface area from which convection is occurring. And its unit is, we know, meter square. And Ts, surface temperature. Can be in either degree C or Kelvin. And T infinity, temperature measured. Temperature of, we can say temperature of the fluid measured at temperature of the surrounding fluid. Surrounding fluid measured at a point far away from the surface. So if you measure in a nearby point, it may have the influence of the hotness of the plate, and its unit is also degree C or Kelvin. Now what is H? Unit of H we can work out very easily. You see, take this equation. So we have the equation as Q convection is equal to H into Q convection is equal to H into AS into Ts minus T infinity. So unit is watts. H, for which we have to find the unit, and for area the unit is meter square, and this is degree C or Kelvin. If you rearrange, unit for H is watt per meter square degree C or watt per meter square Kelvin. H seems very simple, but determining H is very complex. Determining H is very complex phenomenon. H is very complex. We will discuss more on this. This is convective heat transfer formula. So next we have radiation heat transfer. The third mode is called as radiation heat transfer. So the definition goes like this: energy transferred in the form of electromagnetic waves electromagnetic waves as a result of changes in electronic configuration of atoms and molecules. Electronic configuration of atoms and molecules. Unlike other two modes, no material medium is required for radiation. No material medium is required. In fact, it is fastest in vacuum without any attenuation. It happens, radiation occurs fastest in vacuum without any losses. This is how we receive radiation from sun. This is how we receive radiation from sun. We receive solar radiation. In simple words, we receive solar radiation. And there are different forms of radiation, X-rays, gamma rays, etc. What we are going to discuss is thermal radiation, which occurs because of temperature, function of temperature only. That's what is called as thermal radiation. Now let us discuss the governing equation for radiation. So, if there is a surface like this, for example, and temperature Ts and surface area is As, the radiation heat transfer is directly proportional to the fourth power of the surface temperature, absolute temperature, fourth power of absolute temperature of the surface, and of course the surface area. And the proportionality constant is called as sigma into surface area into Ts power 4. And we know this is, what is this? Q radiation is called as rate of radiation heat transfer. Rate of radiation heat transfer. Its units is watts, and AS is area in meter square, area from which radiation is occurring in meter square, and Ts should be in Kelvin only. Absolute temperature of the surface. Absolute temperature of the surface. And its unit is Kelvin only. Here, not degree C. Degree C is not allowed. This is absolute temperature. So it should be only in terms of Kelvin, capital K. So with this, we can find the unit for sigma. Sigma is a constant. K, thermal conductivity, is the property of the material. But in convection heat transfer, H is not property of the fluid. It depends on many parameters: nature of the fluid, nature of the motion, surface nature, etc., etc. Therefore, determining H is very difficult. But sigma is here is a constant whose unit is 5.67 into 10 power minus 8. Now we can find the units very easily. Unit for Q radiation is watts, and area is meter square, and for Ts per 4 is Kelvin per 4. So unit is watt per meter square, Kelvin per 4. This is sigma. So, and if you assume that there is a big enclosure and we have a small surface here and it is emitting heat in all direction, radiation heat transfer in all direction. For this case, Qs is written as Qs is equal to sigma into As into Ts power 4 minus T infinity power 4. If you assume that surface and the surrounding fluid temperature is T infinity and Ts, and here also this should be in terms of Kelvin, and these are all called as black body. These equations are used for black body and black body, and so the equation we wrote in the last slide, this is called as Stefan-Boltzmann's law. This equation is called as Stefan-Boltzmann's law.